cross beds. Those cross beds look a little bit different like this. And these are rather small channel cross bed sets. They're up near the roots of that pine tree up there, kind of rooted into those. So as we come down beneath that, mostly mudstones, clay stones, look down a little bit higher than eye level. We're into this cross bed set here, and then we're back into these channel systems, something like this. This is pretty classic river deposition, channel deposition. And then this up here suggests pretty quiet water. So I'm going to label this a little bit. And I'm going to write HE. And then up here I'm going to write VHE. The HE stands for higher energy. And the V is very high energy, at least in comparison to the lower layer. And then this little succession here, much lower energy. And then we're back into the higher energy scene again. When you start thinking about successions like this, it really makes you wonder why a river system would flux in and out of these types of conditions. Moving in and out of significant episodes with decent current velocities, and then in a really significant low energy settings, suggesting high water or ponding water systems, almost like what you might imagine is occurring behind the dam just up the road here. Yeah, associated with this in the weaker layers are all these crazy swallow nests, swallow holes. And so all the pock marks up there are bird activity in the modern, not the ancient.
So each of those strips, about how many years? Because we're not talking about that it was a low water year, therefore the water was slow.
Yeah, in this scene, you have to begin to start trying to relate this to some deposits that are up at the very north end of the town limits here of Fall River Mills. There's a road just the other side of the river that goes up and flanks the mountains. And that's when we start running into diatomite. And this succession appears to be capped by diatomite in this region. So somewhere up above all this is the diatomite. Its exact position, I don't know how much higher up it is. I haven't seen the whole succession. And so that relationship moves back into this whole scene right up here. And if I had to label the diatomite scene, it would be absolutely a low energy setting. The diatomite is an accumulation of phytoplankton microshells, microfossils. And they're collecting in very fine layers, very fine, thin beds. Now we're going to go see at our next stop. We'll see those. These are freshwater diatomites. Yes, yes. The diatomite is where we get diatomaceous earth from. The diatoms themselves, we'll see this better at the next stop. And unfortunately, the full-out fieldwork hasn't been done on this, but if these are the same diatomites, same age organisms that are seen around Lake Britain, and I expect that they are, we're dealing with about 2.1 to 2.3 million-year-old lake deposits at that position. Now the diatomite accumulations down by Lake Britain Dam, the reservoir's dam there, approach about 600 feet thick. So they represent several 100,000 years of deposition in that area to that extent. That's quiet water, seasonal blooms of phytoplankton, there's shells settling down, and then the repeat of that the next year. You actually see seasonal cycles in the stratigraphy there pretty well. Mixed in with some ash, mixed in with some clays that flushed into the ancient system.
So this is lower than that?
This is older, yeah. But our elevation is an issue, and we'll see that elevational story continue as we go down the hill to our next stop.
So your question was why the different striations? We're talking huge.
We're probably talking almost fixes in the river system in the area that's being recorded here. In that larger crossbed set right there, the first class visit I brought here, we kind of spread out along this, and it was right in that more prominent spot right there. One of my students pulled out a tibia, about that long. Don't know what it's from. I haven't sent it to the proper places to have somebody identify it. It doesn't appear to be rabbit. It doesn't quite have that character. But we actually pulled out it's in my office. I need to send it down. I think Dick Hilton's probably the guy to have look at it, or one of his colleagues at Sierra College. And so we need to find out. It might be that tibia really dates this outcrop quite nicely. But we do think it's somewhere in the Pliocene, somewhere on the scale of 2.5 million years old.
So if you compare the rate of sedimentation here to the really fast rate that dams that you build fill in,
Yes.
that's because of agriculture, because we dammed up high velocity rivers with huge dams.
Yeah, in the perfect spot as well, which is the narrow constriction at the end of the valley, so fill as big a reservoir as we can.
So those dams can get hundreds of feet within 100 years. Of cells filled out.
Yeah, we're filling up Lake Shasta, for example. We're sedimenting in that basin.
But it's a totally different sedimentation rate.
I would say just from the position that the lake goes, you are influencing the pace at which the basin fills pretty dramatically. Rather than having some avalanche block an upstream segment, you now have a dam at almost the confluence of 5 arms of a major river system, the Pitt, the Squaw, the Sacramento, and the Cloud systems, you know. So we place these things very carefully, and nature doesn't. And so, yeah, I like depending on the activity. I think our placement of the Lake Britain, how do I say this? Ancestral damming of the Pitt River was a pretty good placement for nature, for filling up a basin. And we'll see that as we go on to our next stops.